Hi everybody, good evening. We want to thank you for coming out to the observatory on this rainy evening, but it's going to be a fun evening. We have an introductory science bit with our own John Ensworth, and then a special presentation that I'll introduce in just a couple minutes. So we always like to ask who is visiting the observatory for the first time. Hey, oh, welcome, a bunch of people. Well, the observatory this summer is going to be our 20th anniversary. So we're very happy to have been a part of the community, a part of the supporting the schools. We operate as a separate, independent science foundation, even though we are on the grounds here of Berthoud High School, but we tie in closely with the school. We have Scott Kint, who is a teacher at Berthoud High, who does an evening astronomy course that's open to high school students from all of the surrounding schools. So if either you or someone that you know is a high school student interested in astronomy, please talk to one of the volunteers who's wearing these tags, and we would be happy to put you in touch with them because now is a good time to be signing up if you are interested in the astronomy course that's taught here. I mentioned, look for the volunteers. Let's have all the current volunteers raise their hands.
We think we outnumber the people.
Yeah.
You're well covered.
Yep. Well, because it's a lot of fun to volunteer here. Not only you get to hear great speakers, you get to help the kids, the public, learn about astronomy, get excited about math and science, and if you are inclined to want to learn to use the big telescopes, we offer training in that as well. And after you host a group here and they go home for the evening, the telescopes are yours for the rest of the night. So if you might be interested in volunteering here, you don't need any science or astronomy background, but we always welcome new volunteers. And our next training is tomorrow afternoon from 1 o'clock to 3 o'clock. So we'd love to have you come and join us. Got to make the money spiel.
Money, money, money.
Yes, so first of all, I'll let you do your Vanna White impression. We have various...
Apologies to Vanna White.
We have various things for donations, and the comment you heard back there was from our treasurer, Mark.
Write his name down. I'll send you his home address too.
Yeah. And there is a donation box back by the door. I hate to be bringing up the need for money, but we are a nonprofit, all-volunteer organization. And since we have so many school groups that come here, because they're a school group, they're not able to always financially donate, it's very helpful when the community does, and much appreciated. Are there any other announcements before we go on? Okay, well then, without further ado, I will introduce our volunteer, John Ensworth. He has been a teacher of astronomy and science topics, and he currently works for NASA in the education department. And we are happy to have him be giving an introduction to current topics in astronomy.
Thank you very much. I keep these short, but they just a little warm up to bring you up on to speed on any current news in astronomy. And so this week, so as not to step on any of the material that we're going to hear the rest of the evening, we're going to talk about something called fast radio bursts and give you a gravitational wave update. This is sort of becoming my favorite topic. It's the third time I've had it in an update here. So what is a fast radio burst? These are very powerful but very brief radio pulses that were observed. And for a while there, we didn't have the technology to even really see these out of the noise. They last just a few 1/1000th of a second, a millisecond, to even a fraction of a millisecond. Really short, but pretty powerful. Of course, powerful is relative. You get about the power 1/1000th of that of someone on the moon with a cell phone trying to make a call. But that's pretty good when it's coming from someplace far out in the universe in a different galaxy. What is really neat is that we have discovered a few of these that are repeating. They occur again and again. We estimate that there may be up to 10,000 fast radio bursts per day over the entire sky, but they're hard to nail down. So one of these repeating ones that have been studied in a little more detail is fast radio burst 121102. 3 billion light year away galaxy that doesn't have a lot of the heavier elements than hydrogen and helium in them. And what helps us kind of figure out where this might be coming from is that there's also a radio source coming from this direction. There's a glow. And so putting that together, one of the models that we're playing with is that this fast radio burst, or FRB, could be coming from what's called a magnetized neutron star, or a magnetar. And that created a superluminous supernova, super bright, much brighter than normal supernova, 10 times more powerful than the standard ones. And these very strong magnetic fields are spinning on the millisecond time scales. And just for a few decades, you'll get a few extra bursts after the early formation of the magnetar. So it's a short-lived phenomena. It's got the right energy source level and timing that we may have an explanation of these little guys. Gravitational waves were first observed just in the last about year and a half, announced. In the new run, they've upgraded the equipment to be more sensitive. They're working continually on ways to take out noise and get these things hearing things that are a weaker signal. And we have 3 observatories normally operational to allow us to figure out what part of the sky this has come from. There's a little tiny timing difference between the 3 sites in where the waves impact the Earth. But only 2 are working. The 3rd one had gone down for a little alignment problem just, I think, minutes or an hour before this arrived. So we're not really sure where this came from. We expect that this merger was a merger between a black hole and a neutron star. So it's the first one we've seen. It's a mixed object like that. We've seen 2 neutron stars. We've seen double black holes come together. We would expect a big flash of light, but none of our observatories that look for transient bright flashes saw anything. So we do know of at least that. Someplace in the sky, we've seen this first weird other mix. We have 5 other candidates that are already being worked on this month alone. So with the increased sensitivity, we're starting to see a lot of these. We are getting to the point where we can take a look at the statistics of how likely it is the signals that we're seeing of maybe 2 black holes, or neutrons, 2 neutron stars, or black hole neutron star coming together might be just an accidental detection or something popping out of the noise. And it's helping us get even more confident in the signals that we're seeing with the gravitational wave detection systems. So you can help now. Anybody familiar with Zooniverse? This is a citizen involvement science project where you log in and create an account, and you can go with your eyes on your home computer whenever you want, search through data sets. They give you a little training, and you look at the data and you look for possible signals. And all sorts of things have been discovered in astronomy through these distributive computing systems using your brains as computers to help astronomers comb through the ever-increasing terabytes and exabytes of data that are being produced by these surveys. So you can help with Gravity Spy. If you don't want to write this down, just Google Gravity Spy. You'll get to that site and go through a little training and contribute. Now, you don't have to worry whether you are making a mistake, because they put the same data out in front of 10, 20, 30 other people, and they only consider it something significant to pass on to the next level if a number of people agree with each other that that is what's being looked for. So the entire weight of science is not on your shoulders. You're just contributing. And they used to, with the gravitational waves, secretly pass papers around and encrypt zip files and send things and discuss it. Okay, do you think we got it? Because it was a brand new science. But now we have enough confidence that the signals we're seeing are candidates, at least. You can just now, if you have an iPhone or any iOS system, get GW Events app, and you can set up notifications, and your phone will buzz every time these detect. Yep, and I've already been buzzed twice today, and so I can see gravitational waves being detected live. So pretty fun, and then you can go through the past list of candidates on the app. So yes.
Where are the 3 observatories? Gravity.
One is in Louisiana, one's in Washington State, and one is in India, I think.
I know the first 2, I don't know what the third one is.
Yeah, I think the third one might be India.
Wasn't there one in Turin, Torino in Italy?
Could be, and maybe India's coming online. That's the 4th one that will be coming on. Yeah. All right, any questions? That's it. That's all I got. All right, we're going to switch over technology and bring up our main speaker tonight.
Well, let me do an introduction to our main speaker tonight, again, Durga, while they trade off the microphone. His talk tonight is actually going to be a good tie-in with our June presentation as well. Every 3rd Friday, we have a speaker here, and so Dan is going to be talking about exoplanets. So planets that are orbiting around other stars other than our sun, other solar systems. And our June talk is going to be about NASA's Kepler Space Telescope mission and Kepler's search for exoplanets. So this talk tonight will give you a good foundation and knowledge about exoplanets in preparation for next month's talk as well. So Dan is actually going to be repeating a nationally known presentation that he gave when he was awarded the Carl Sagan Medal for Educational Excellence. That is awarded by the American Astronomical Society and the Division in Planetary Science for an astronomer who has, throughout their career, done a good job of communicating science to the public. So we're looking forward to hearing a reprise of this presentation that he gave in honor of receiving that award. So Dan originally came from Michigan and then was a grad student at the University of Florida, where he got to watch 27 space shuttle launches. And I've known Dan for almost 20 years because we had both at one point been at the Southwest Research Institute in Boulder, and that's where Dan has been for about just over 20 years now. And in watching all those space shuttle launches, got interested in being an astronaut himself, and he came this close to being chosen by NASA, but as you know, it's very competitive to grow up and become an astronaut. However, he has been chosen as a future astronaut payload specialist for upcoming to be dates determined, space flights on Virgin Galactic and Blue Origin. And if you enjoy Dan's presentation tonight, I encourage you to Google Dan Durda and TED Talk, where he has a fun TED Talk presentation about spaceflight as well. So, did I miss anything?
That's great.
Okay.
Awesome. Thank
Well,
you.
Let's welcome Dan Durda.
Awesome. Thank you, Andrea. And is this too loud? Am I talking in the right spot, or is it giving me a little feedback? Okay, that's cool. That's great. Thanks again. Thanks for having me here. It's great to be back. I think I was here about 5 or 6 years ago and talked about all that training for the suborbital space flights. Today I wanted to talk about, this is a talk about first love, basically. What got me in the field in the first place is this topic of planets around other stars. When I was interested in it back then as an undergrad, there were no known planets around other stars. It was all in the future. It was all TBD, and it was all about how are we going to do this. But now we know we're living in quite a different world, and we're living in a very, very different galaxy now. As Andrea said, this was the talk that I gave for the Sagan Medal Award. I did this. It says at the Boeing Education Center. It's a little bit bigger than this, but that's the one. It's Griffith Observatory in Los Angeles. That's where the spot I chose for the particular talk, and it was. I didn't see much need to repackage. I mean, there's a few little things that are not so much out of date that just have been added to, but I thought we'd continue along. As Andrea said, I grew up in Michigan. And I remember as a kid, I'm looking for people in the audience here. Yeah, I see somebody about the age I was when I was getting interested in this with my dad's binoculars, looking up in the sky and seeing, in this case, the moons of Jupiter. This is a kind of a binocular shot of what the moons of Jupiter look like in the binoculars. And I knew that. I knew what I was looking at. I knew I was looking at the moons of Jupiter. It's in all the astronomy textbooks. But then, of course, at that age, by analogy, I was scanning the sky all over the place and spotting similar-looking sort of pairings around, stars here and there. And in my mind, I'm thinking, you're starting to look in close and stuff. Maybe, starting to see planets around other stars. I thought it was a cool thing. I'm seeing planets around other stars. Not to be, of course, unfortunately. But that wasn't supposed to happen. Pardon me. Hold on a second. Let me repark that. Okay. I didn't have it clipped on well enough. Or it was clipped on well enough and I just made it exit prematurely. There we go. Oh, I understand why. Tell you what, I'm going to do it this way. That's what they say. Do that. Okay, back in action. So, not planets around other stars, but I had this beautiful backyard. This is an actual picture of my backyard growing up in Michigan. I grew up in the country, out in the middle of nowhere. The skies were dark, and I had wonderful skies, and spent much of my youth just laying on my back in the grass with my dad's binoculars, scanning the sky. And my favorite patch of sky of all time scanning through is the summer triangle. Just summer Milky Way passing over the Michigan sky. There's Vega. There's where the heck is, I'm too close to the screen there. Okay, boom, boom, and then I think right there, dancing through the leaf in the tree, is the other end of the triangle. And I would sit there on my back, looking right through the Cygnus star cloud here, and it's a great place. I mean, just a great place to scan with binoculars. Stars galore, and I would just look and think, and all those stars, and how many of those stars have planets, right? You'll want to remember where we're looking there. That'll come up a little bit later on. That's how I spent my youth, and that's what I got interested in coming out of high school and heading toward undergraduate school at the University of Michigan. Around this time, 1980, Carl Sagan's Cosmos came out, and that's right when I was, cued to this. What a great series to come out at that point in my life. When I was primed to want to be interested in this sort of stuff, and that's what convinced me that I wanted to go and get a PhD in astronomy. It was this television series. And I don't think it's by coincidence, because of Carl's love of that particular topic, that I myself also got interested in this concept of planets around other stars and extraterrestrial life. So that's what did it for me. So I'm going to set up a little bit of A little bit of context for you here. Just go ahead and pass those out and spread them back. I want people to have these in their hands. This is what you're going to see on the piece of paper that you're going to get. It's a to-scale plot of the inner part of our solar system. As you get this piece of paper, if you have old man eyes like I do, you may have to take your glasses off or put them close to your face or something. You will see just above the word sun, there is actually a little tiny dot there. And that tiny dot is purposely hard to see because it is to scale the size of the sun relative to the orbits of the planets that are plotted out here. Okay, so you've got the 4 inner planets, Mercury, Venus, Earth, and Mars. And then down here at the bottom of the little figure, there's a little arc for the orbit of Jupiter. If you can just kind of imagine on the piece of paper, imagine extending that out around all the way around. But that dot is purposely small because it's to scale. Okay, just barely about the size of a dot on an eye on a printed page. Okay, so why did I do this? I did this because noodling around in back in the 1979, 1980 on my own. I'm sure people had figured this out before, but for me it was a new discovery. I was just playing with the numbers one day, and I happened to realize that. Let's go back here. I happen to realize that if you calculate out how many inches there are in a mile, okay, it turns out by numerical coincidence to within about 0.7% error, there are as many inches in a mile as there are astronomical units in a light year. The astronomical unit being the average distance between the Earth and the Sun. And so if you set this scale where 1 inch is an astronomical unit, then 1 light year would be a mile. And so with this scale picture, you now have an idea of being able to set to scale how small the planetary systems are around stars compared to how far stretched the stars are apart from each other. So hold the piece of paper in your hand, look at it, picture that dot that represents the sun, and now picture another one just like it, 4.5 miles over in that direction. Okay, that's Alpha Centauri, the next nearest star. 6 miles over there is another dot like that, okay, Barnard star, okay. 8.7 miles away over that way is Sirius, okay. So every several miles, imagine another piece of paper like this with another little set of circles of various sizes that are going to represent the planets around those stars, which, as you're going to see, we now know that almost every star has planets, okay. That's the kind of separation, and so imagine somebody holding a piece of paper like this 4.5 miles away, how you can barely see a person 4.5 miles away, let alone that little piece of paper they're holding. Gives you a sense of scale for how crowded in the orbits of the planets are around their stars. That's the difficulty of this problem, okay? People have been thinking about this for 2,500 years. The ancient Greeks were already primed to the idea that the stars are other suns, and they may have planets orbiting around them. Giordano Bruno was burned at the stake for the heresy of suggesting that that our system as we know it here is not unique. And here's something he wrote, that there are countless suns and countless Earths all rotating around their suns in exactly the same way as the 7 planets in our system. Okay, I mean, already people have known this for quite some time, just sort of intuited it. But we haven't had the technology until just recently to do it. Christian Huygens, the discoverer, really the person who, the discoverer of Titan, but the person who really first clearly understood the nature of the rings of Saturn. He had this fantastic book that he wrote called The Planetary Worlds Discovered. It was, you can see the rest of the little subtitle up there, Conjectures Concerning the Inhabitants, something of the other planets, the other worlds. And he goes on to talk about, by analogy again with, you have to imagine, 1600s, 1700s, European notions of what life on other worlds will be like, imagining what that life will be on all these other worlds. And there's lots and lots of discussion about this. But I love this discussion here where he's, by analogy now, talking about how the stars are other suns. And by analogy with the planets in our system, then why don't every one of these other, stars or suns have as great a retinue as our sun, of planets with their moons to wait upon them? He says, no, there's a manifest reason why they should. For if we imagine ourselves placed at an equal distance from the sun and the fixed stars, we should then perceive no difference between them. For, as for all the planets that we know attend the sun, we should not have the least glimpse of them, either because their light would be too weak to affect us, or that all the orbs in which they move would make up one lucid point with the sun. Okay, it's a fantastic quote describing basically what I just said with this piece of paper a little earlier. So this is, written in the late 1600s, published in 1722. Amazing stuff. So, how do you actually go about cracking this problem? It's very difficult. How do you do it? One way you can do it is to recognize that our simplistic description that planets orbit stars isn't exactly right. It's planets and stars orbit each other. They actually orbit their common centers of mass. I'm going to show you Pavel from Poland here doing his hammer throw in a sporting event, but look what's happening as he's doing that. Watch the motion of his body, right? His body is actually orbiting the center of mass of that ball, of that hammer that he's throwing. So here it is, basically, right? This is a star orbiting the common center of mass of this star-planet system. Now, if you zip away and kind of imagine what this star is now like relative to the background stars, of course, all the stars are out there moving relative to each other. But if you can track the motion of that star over time, you're going to see it doesn't just move in a straight line. If that star has a massive planet orbiting it, you're going to actually see that star wobble through space as it moves, as you track its motion, right? That characteristic wobble is a sign, a signature of an unseen planet orbiting that star. That's one clue that you can have that you've got something going on there. And it's not just the mere existence of the planet, knowing what type of star it is and having some knowledge of what the mass of that star must then be. You can then, based on the size of the wobble and the period, you can start by Kepler's laws to get some clue, some idea of how massive and how distant that planet must be. So you can start to get some character. This is called the astrometric method. It's actually been used. I myself, as an undergrad, sat there with glass telescopic plates and the old-fashioned mechanical measuring engine lining up a spider web crosshair to measure the proper motion of a dim red dwarf star, looking for motions like this. Didn't see it in that star, but people have done this. People have done this for Barnard star in the past. When I was growing up, as an undergrad, reading about all this, before we ever knew of any exoplanets, there was one suspected well, I shouldn't say one, there was one well-known suspected exoplanet around Barnard star, the second nearest star, because of this method. Now, it turns out that what was then thought to be something wobbling probably wasn't, but now we have detected this for other systems. So the astrometric method is a pretty straightforward way of doing this. Now, what about just like bypassing all this indirect stuff? What about just going in there and looking at the star and looking, as I did through my dad's binoculars, and just seeing a planet around another star? It's a little bit difficult, as you might imagine, because you're looking for the dim reflected light of the planet next to this brilliant searchlight. It's like looking for a firefly sitting on the rim of one of those big car dealership advertisement lights that beam the thing up into the sky, right? Imagine one of those shining right at you, and you're looking for the little firefly that's sitting on the rim of it. It's a pretty tough problem, okay? So here's the same idea that I had before. We've got the star and the planet orbiting around each other, okay? Now, I start all these images out the same way, so you can kind of, we're all in a common sense here. So now let's zip out. Now, what's this going to actually look like through the telescope, okay? You've got your Jupiter-like planet, say, orbiting a sun-like star at 1 astronomical unit. Now, of course, this is an idealized sort of cartoon version, right? What you'd actually see in a telescope is probably something maybe a little bit more like that, actually, okay? So, yeah, good luck finding that planet, okay? That's the nature of this problem of direct detection. That's why you can't actually really do it as simplistically as it sounds. But it turns out you can do it. In this case, if you actually calculate, okay, how much light is being reflected off of Jupiter compared to how much light the sun is emitting, if you're out there at the distance of some of the nearest stars looking back at us, the sun is outshining Jupiter in the visible part of the spectrum like this by a factor of like 330 million to 1, okay? And that's a good luck doing that with any sort of optical system that we have. 330 million to 1 is pretty tough. Here's the nature of that problem. In the optical part of the spectrum, the visible part of the electromagnetic spectrum that we're observing, this is pretty much the case. The sun is up here, you know, many, many millions of times brighter than the dim light reflected off of the planets. What we've plotted here are something called black body curves. This is how much energy in that part of the electromagnetic spectrum these various objects are either emitting or reflecting. Okay, you are emitting a black body curve of radiation, electromagnetic radiation. They're only dependent on your temperature. Each one of you sitting here in this room is emitting the equivalent of something like about a 100-watt light bulb, mostly in the infrared, because at 98.6 degrees Fahrenheit, that's where the peak of your electromagnetic radiation emission is. You're all giving off X-rays too, but not many of those. Thank goodness. Okay, if you had a fever high enough to start emitting a lot more X-rays, we'd be in trouble. So here in the visible part, the planets are pretty much only reflecting the light from the star. But if you were to move off into the infrared portion of the spectrum, especially deep into the thermal infrared, the planets start to get bright again. It's not that they're just merely reflecting the light from the sun, they're actually starting to give off their own emissions, because this is where their part of the black body curves are peaking. Especially a big planet like Jupiter, which is still to this day emitting more infrared radiation from its interior than it's getting from the sun, because it's still leaking out all of that gravitational potential energy that it gave up in its formation, during the gravitational collapse of its formation. So Jupiter is pumping out all this infrared. If you go off into this part of the spectrum, the picture becomes a little easier. So instead of something like this in the visible part of the spectrum, the problem becomes much easier in the infrared. I think this was supposed to be a movie. There we go. In the infrared band, though, now the star becomes dimmer because it's giving off most of its energy in the optical part. The star becomes dimmer, the planet becomes brighter, and you might actually be able to reduce that brightness contrast, not from maybe 1 in 330 million, but maybe 1 in 50,000, say. Something like that. Okay, that's not so bad. But there's another trick. You can even play the trick even better. If you pick the star that you're looking at well enough, if you pick a young star, okay, stars get brighter as they get older, not dimmer. They get brighter as they get older. Young stars are a little dimmer. Any big giant Jupiter-like planet that's forming around that star is going to be even hotter in its earlier stages of formation and giving off even more infrared radiation. So if you want to do this direct detection method, the thing you do is you look at young stars that are intrinsically dimmer than the sun, and you look for the forming planets, the forming gas giant planets in those systems. And then you're thinking not maybe a brightness ratio of 1 in 330 million, not 1 in 50,000. You can bang this down to something like maybe like 1 in 7,000 or 1 in 8,000, something like that. And that's a brightness ratio we can pretty easily do. And in fact, we've done it. Here is a picture of a real star. This is HR 8799. It's a young star, 30 million years old. 126 light years away in the constellation Pegasus. And here we are looking in the infrared portion of the spectrum and simultaneously blocking a little of the light of the star out with a little finger inside the telescope. And I'll tell you, there is a planet visible here in around this star. I'm going to give you a little help because there's other stuff going on here, but there is a planet. And it's that right there. It's that little blob right there is actually a directly observed planet around the system. This is, in fact, one of 4 giant gas planets orbiting this star. And in fact, this stellar system here is the very first system where we've ever been able to actually watch the orbital motion of the 4 planets around the star over time. So we can actually see it happening as it goes. And that's one of the 4 planets, the brighter of the 4. Now that's really cool because now you not only just detected the planet. When you can get the light from the planet, you now have the ability to start to learn something about the planet itself. Because once you have the light from the planet, you can play some games like spreading the light of that out into its the component spectrum of colors. And in the case of the planet, so what we've done is we put the spectral slit across the star this way. You're spreading all the light of the star out. And then again, remember where the dot of that planet was, right up in there, spreading that out. That bright that little bar of stuff going right through there is the spectrum of the planet. I'm going to put it out flat here for you. So there's all kinds of other ghosts, you know, the diffraction rays around the star and all that kind of stuff. There's the light of the star itself spread out into the spectral colors. But right through here, that little bar, that little beam right through there is actually all the light of the planet spread out into its component colors. And if you carefully analyze that across the CCD and make the plots, you get this beautiful little spectral curve, which tells you things like how are some of the gases. Well, first of all, it tells you that there are gases in an atmosphere around that planet. As the sunlight from the star, you know, transmits through the gaseous atmosphere and then reflects back out through, some of the wavelengths of the sunlight are gobbled up by the component molecules in that atmosphere, and the ones that are missing tell you what molecules are there. And it turns out in this case, it's a massive Jupiter-like planet with tons of water vapor in the atmosphere. Water vapor, a little bit of CO, carbon monoxide, and a little bit of methane. So not only do we know there's a giant Jupiter-like planet around the star, we know what its atmosphere is made out of. And that's pretty phenomenal. Think about that. I mean, how far we've come. It's just amazing to me. Okay, so that spectra, the astrometric method of looking for planets around other stars works best. It works in all situations, but it works best if by accident the plane of the planet's orbit around that star is kind of tipped face onto us, because then you see the biggest wobble of the star as it's moving through the sky. Okay. Now, if by chance the plane of the planet's orbit is tipped more in our line of sight, then the star wants to be going around kind of, you know, first toward you and then away from you, toward you and away from you. That offers up another possibility. So again, here's our little starting situation, the same planet, the same star system. But now we're going to imagine that we're looking at this system from the side. And here now you see where you're going through the situation where sometimes the star is coming toward you a little bit and then away from you a little bit. The light from it's blue shifted and then red shifted. Blue shifted and then red shifted. What that does is, if you were to look at the spectrum of the star itself, the spectral absorption lines in the atmosphere of the star get red shifted, blue shifted, red shifted, blue shifted. Okay? So again, even if you can't see a planet directly around that star, you know there's something orbiting it by watching those spectral lines shift back and forth. And if you do it for real, here's what the solar spectrum looks like for real. That was a kind of cartoon version, but here's the calcium H and K lines, for instance. Here is the sun spectrum spread out in great gory detail, and you can see all these deliciously wonderful iron lines all through the solar spectrum. So if you're looking at the spectrum of other stars, you've got lots of lines to look for. But what you're looking for there is a very, again, difficult nut to crack technologically. If you imagine now Jupiter orbiting our sun, not where it is, but maybe at 1 astronomical unit where the Earth is. And now imagine what that's doing to the sun. That's tugging the sun around once a year as Jupiter's orbiting it. So the sun's coming toward you and away from you and toward you and away from you. And you can calculate how fast it actually has to be in that situation. It's about something like about 60 miles an hour, actually, it turns out, is sort of the speed that the sun is orbiting around that common center of mass in that situation. And we can detect actually that 60 mile per hour spectral shift pretty easily. We have the technology for that. It's a little harder for something like the Earth. The Earth tugging the sun around its common center of mass for real is incredibly small. It makes the sun move about 9 centimeters per second on this little tiny little orbit that it does once a year. And 9 centimeters per second is way beyond what we can detect right now. But this is something we can do. Okay. Now, let's take that even further. Let's imagine now that stellar system is not just tipped roughly in our direction, so it's coming toward us and away from us. What if this stellar system is tipped exactly in our line of sight to the point where, once in orbit, we actually see the planet and the star eclipse each other? If you watch this little cartoon here carefully, there the planet went behind the star, boom. Watch that little black, little eclipse going on there. Little eclipse. I'm going to zoom in. I slowed it down. Now we're going to zoom in here. This is what we're looking for with the Kepler Space Telescope. We're watching for those little transits when the planet orbits around the star. By chance. We don't know which ones are going to be doing this. We're just going to be staring out there and watch for these little eclipses that go on. And it turns out that that's the method by which most planets around other stars have been found. So back in 2008, Venus transited the sun, and here's an actual plot of the brightness difference across the disk. And I just made a little cartoon here of what that star, if it was a star from a distance watching, you'd then see the, things change. And you're looking for that little eclipse dip in the light of other stars. That's what Kepler was all about. And I'm not going to tell you too much about the details of the Kepler mission because that's next month's talk. We'll let next month's speaker do the details of that. But it's basically a space telescope. It's a space telescope that was launched in March of 2009 and spent a whole bunch of time staring at one particular patch of the sky with this fantastic camera system. This is basically like a 96 megapixel camera that was built. It was 42 CCD detectors on the basically where you might expect the secondary mirror to be for the telescope, or I guess even the tertiary mirror. This detector plane, a whole bunch of CCDs, really nice images. And the basic idea was Kepler would be out there, not orbiting the Earth, but orbiting near the Earth in its own independent orbit around the sun, just staring at one patch of the sky continuously and recording the brightnesses of the stars in that patch of time, just beaming down brightness, 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 brightness. And then you just, with your computer analysis, you just watch the brightness of every star. And you're looking for these little, like maybe once every 3 or 4 years, for a couple of hours, the brightness might dip by 1% and then come back up again. That's what you're looking for. That's what Kepler is all about. And here's the fun thing. Where did Kepler choose to look? There's the summer triangle, and there's the Kepler search field. So back in this time, NASA decided to solve my problem for me and actually find out how many planets are up there in that patch of sky that I used to stare at as a child and wonder. And it's just poetic for me. It almost brought tears to my eyes. It was like, oh, now we know. And now we know there are thousands and thousands and thousands of stars in that patch of sky that have planetary systems around them. I'm going to step through a couple of slides here that are going to try and impress upon you what Kepler did. This is a plot that was made, a little diagram that was made very, very, very early in Kepler's mission, as it was just getting started in detecting things. What's plotted here, these are all to scale, and right here is the key to the scale. This, imagine being our sun, our G2 main sequence star, and you'll see a little black dot right in there, which would represent the disk of Jupiter passing across of the disk of the sun if you were looking at us from a vast distance away. Now, you can't see it. I'm going to look to see if I can even see it when I get close here. It's on the original, but I'm not even seeing it projected here, so you're not going to see it. But on the original, there's a little sub-pixel which represents the Earth actually in there as well, but I can't even see it close up, so there's no way you're going to see it. Okay, anyway, so that's what our system would look like. Here to scale are the disks of some of the other stars that are in that search field that Kepler was looking at, with the size of the disk of the stars to scale relative to our sun, and the color temperatures also kind of plotted to scale. Some of the stars are bigger and hotter and bluer than the sun. A few of them are a little bit dimmer. Most of them are pretty close. The whole point of the Kepler mission is they wanted to target primarily sun-like stars. The whole point was to look for planets around sun-like stars, Earth-like planets around sun-like stars. That was the whole idea. So here you see there's a whole bunch of little black dots. Each one of these has got a little black dot in there somewhere. Some of them are more prominent because they're bigger planets. In some cases, you'll see multiple black dots, and that's illustrative of the case that not only are we finding planets around stars, we're finding planetary systems around other stars. And every single one of these is a planetary system detected by Kepler in the very earliest days of its mission, before it even barely got going. Here's another way to look at it. Again, our solar system to scale. Here's Mercury, Venus, Earth, and Mars orbiting around the sun. There's Jupiter, Saturn. And each one of these now, to scale, is one of the little transiting planetary systems detected early on by Kepler. And what this should impress upon you is Kepler did exactly what we wanted it to do. It gave us context for understanding the variety and the scope of other planetary system architectures that can be out there. Okay? These are not hypothetical little things. Every single one of these is plotted to scale with the exact parameters and the orbital periods and everything for planets around other stars up there in the Kepler search field. And the first thing you'll notice is the observational bias in the Kepler, this transit method of finding things. You are biased toward finding big planets close in with fast orbital periods. Okay? So there's a bit of a bias here, but it also does directly tell you that there are some very distinctly different sorts of planetary system architectures that are going on. And it immediately presented a very big puzzle to those of us, not me, those of us in the planetary community who are trying to understand how our planetary system formed based on what we see in our planetary system. You, of course, tend to generate ideas that tend to make you think that all planetary systems should have this kind of similar architecture. And then we start finding the equivalent of something like Jupiter orbiting in 1/10 the distance of Mercury from its parent star. And you're like, how does that happen? You know, how do you have the gaseous, the very volatile hydrogen and helium and things like that being able to survive that close in to a parent star during the formation period? And it caused us all to go back to the drawing board. And it's like, well, okay, now how do you actually do that? And it's fantastic because, again, it put our planetary system in context, and it caused us to have to go back to the drawing board and learn more about the planetary formation process. And now we do know that planets don't necessarily form, where you see them is not necessarily where they formed, especially in our planetary system. Jupiter and Saturn and Uranus and Neptune have probably migrated around quite a bit from where they were originally formed. Go ahead.
So what percentage of the stars would you actually get a transit of compared to the number of stars that are out?
Yeah, exactly, tiny fraction, because you can imagine, right? Imagine that geometry. You're looking for, picture that dot again on the piece of paper, right? That very extremely narrow angle of chance lineup to get that planet to pass in front of that little dot. Basically, it's a tiny, tiny, tiny fraction. And so the amazing point is that for all the thousands of transiting systems that Kepler saw in that field, that's just the tiniest of fractions of the planets that actually are out there in that field. Because most of the stars you're not going to see winking out because the planets are orbiting in a way that you don't see. So yeah, tiny, tiny, tiny fraction. The odds are very slim. So yeah.
What's the order of magnitude?
I didn't actually physically answer your question. I mean, it's like what, 1 in 10,000, you know, 1 in 100,000. Yeah. Okay, another way of looking at it. Okay, plotted here. I'm not the artist who did this. I wish I was, because whoever it was a genius. I got to look close because I want to show you to scale a couple of things here, and I got to get close enough myself to find them. Okay, there's one. Where'd the other one go? It's got to be. I'm looking and I don't see it. Oh, yeah. Okay, there's that one. Yep. And there. Yep. Okay. I got to come close so I can then point them out from the distance. Come on. Where is it? I'm missing a planet. Well, I'm doing this in real time. Okay, well, we'll find it later. Maybe one of you will spot it. Okay, so plotted a different way now. Again, these are the same planets that we've seen before in the Kepler set of data, except now we're looking here at only 1/4 of all the planets that have been found. And this is not even all of them because I'm going to scan down a little bit. These are organized in two different ways across the plot here. Planets that are more dense are up on the upper part of the plot. Planets that are less dense are toward the bottom part of the plot. So all the like nickel, iron, metal rich, rocky planets are up high, and the light, fluffy gas giant sort of things are down low. The colder planets are over this side. The hotter planets are over on that side. And they're all plotted to a scale by size. Of course, we don't know what these things actually look like, so the artist has taken some license here, but the idea is to basically, kind of give you a sense of the variety of scope of things that might be out there. But in here, to scale, just so you know, are some real things in our system. Our little blue, geez, I just stood here and I looked for it, and now I've lost it again right in front of my face. Oh, there we are. There's home right there. There's Earth, okay, to scale. There's Earth. There's Venus. There's Mercury. And what I was looking for, of course, was Mars, and I lost where Mars went. So if one of you spots Mars, let me know. I can't find Mars. It's on here. I just can't find it. Anyway, so you'll see by note, of course, that surrounding Earth are a whole bunch of other planets in here that Kepler has found that are roughly the kind of same density as the Earth and the kind of same temperature. By definition, these things that plot closest to Earth on this plot are the most Earth-like planets that Kepler has found. And so oh, there you found it. Great, thank you. There's Mars. Very good. So again, Mars, a little colder and a little less dense than the Earth compared to, over, why do I keep losing the Earth right there? Okay, anyway, so, but I didn't even do all of them yet. I'm going to scan down, so I'm just going to pause down. This thing makes a little bit jump. So this is just 1/4 of all the planets that have been found so far, okay? Here's our own Saturn. Here's our own Jupiter. Here's Neptune. Here's Uranus, okay? Lots. So again, remember the dense things are up there. So most of the terrestrial type planets are way up at the top. They just went off the list already.
So did you actually observe planets with rings like the guy there?
So far, no. So far, no distinct, definitive transiting photometric detection of rings. These were put in, other than our own Saturn, these were put in to just sort of suggest that some of these may have ring systems. I take that back. There has been a super ring system that has been detected by Kepler. There is, yeah, there's one planet with what's called a super ring system. It's almost more like a disk than a ring system, but it's a very distinctive disk. Yes, I take that back. There is one. Okay, so anyway, whole bunch of planets around stars out there, okay? We really do live in this sort of Star Trek galaxy where just about any planetary system you can imagine probably exists out there. There's a vast, amazing stage for the play of life out there, which was, of course, what kind of got me into this field in the first place was, that's why I say it's a story of first love, because even though I don't do this research today, I'm more of an asteroid guy, this is what got me in the field, this romantic thought of living in a populated, rich, diverse galaxy like that. Just amazing. So here are some of the, just to scale here again, early on in Kepler's mission, one of the very first multi-planet systems that was discovered was surrounding Kepler 37, with 3 kind of Earth-like-ish planets that are all orbiting well inside the orbit of what would be the equivalent of the orbit of Mercury in our solar system. There's a little tiny Kepler 37b. At the time it was discovered, it was the very smallest exoplanet ever discovered at that time, about the size of our moon, okay, which is a phenomenal technological achievement if you think about it, to spot something of a disk the size of our moon passing in front of a solar-like star out there, hundreds of light years away. Phenomenal achievement and good proof that Kepler is capable of detecting Earth-like planets around other stars. So Kepler 37 is, you can see, it's right sort of in this range of Earth-like size and mass. It turns out that statistically, when you correct for all these observational biases, and you look at what are the most common things that Kepler is actually seeing, corrected for all those biases, it turns out that most of the planets around stars in the galaxy are probably these super Earths. These things that are 2 or 3 times the size of the Earth, maybe 10 times the mass of the Earth, not quite big gas giant Neptunes or Uranuses, but something bigger and more water-rich and gas-rich than the Earth. This is probably the most common type of planet out there in the galaxy. Another way to look at it is thinking about all of the various planets that have been found around their stars in the equivalent of where the Earth is orbiting around our star in terms of temperature sort of region, the habitable zone, if you will. Planets that are orbiting where you could have liquid water. Okay, Kepler 22b is, I think, a system something on the order of 620 light years away, if I remember correctly. I'm probably remembering that wrong. This was the first one to be discovered in the habitable zone of its parent star. And then since then, a whole bunch of other ones. Kepler 186f, this is one of several planets orbiting in this system. And this particular one is orbiting its red dwarf parent star at a position from its parent star that puts it at the place where the temperature is exactly like here on Earth for that particular planet. So there's a very interesting possibility for that guy. But not all of these are going to be Earth-like planets. Okay, Earth-like, when we use that term in this context, usually just means Earth mass or Earth size or both. Not necessarily that the environment there is going to be conducive to life the way it is here. So I'm betting that many of these are going to be pretty yucky planets to be on. This is just an artistic representation I did, digitally generated with some photographic elements in there to represent this noxious, yucky atmosphere that you probably wouldn't want to breathe with not a speck of life any place on this particular planet. But we know, again, that many of these worlds are water worlds, water-rich worlds. Permanently overcast, probably, very water vapor-rich atmospheres with these surfaces entirely covered by water oceans. So take a cruise on a Princess cruise line up the coast of South America and look out there for days on end at the ocean. And that's probably what you're going to have for a lot of these planets around other stars. There's a big variety out there. And again, the habitable zone, this concept that if you've got your planet at the right position relative to its star, the temperatures will be maybe conducive to having liquid water on it. If you come a little bit too close, things get too hot and that liquid water is boiled away. If you go too far away, the water freezes and you have ice on the surface instead of liquid water. But depending on the type of star and the age and the effective flux where you are, Kepler has actually found several planets in the habitable zone of their stars. So things are looking pretty bright there from that perspective of not just Earth-like in size and mass, but Earth-like more in its climate as well. So, and this is already 3 years out of date, so because I gave this talk in 2015.
When did Kepler go up?
March of 2009. I think March 9th. You may remember that. I think it was March 9th.
So
March
had
9th,
they
yeah.
definitively detected another exoplanet before Kepler?
Yes, the very first exoplanet system definitively detected was, ironically, that pulsar system, where you have planets orbiting a pulsar, of all things, this rotating neutron star remnant of a supernova explosion. So probably these are the exposed cores of gas giant planets that were orbiting that star before it went supernova. So ironically, the very first system that was definitively detected was probably the most inhospitable, like these charred remnants orbiting a neutron star. But just before. I mean, this is I don't remember the exact dates. I think mid-90s, something like that. I think one of the first transiting systems detected from the surface of the Earth was 95, somewhere around there. So this might have been 90.
When the first one was detected,
Yeah.
all of a sudden there's
Well,
billions.
and it's because of Kepler. It is because of Kepler. I mean, it's not that we haven't detected many now from ground-based studies with transiting. I mean, the telescopes out here in the garage, right, of this observatory are fully capable of doing this transit method of detecting planets. You guys can do your own backyard transit detections, right? It's just that with Kepler at that really high level of precision, just absolutely revolutionized things. So. I wanted to make one point about this habitable zone thing, though. The conceit has always been that we're thinking about the traditional habitable zone, the traditional ideas of having an Earth-like planet with liquid water on it. Well, we now know that this concept of the habitable zone is kind of almost useless, because now we know in our own solar system, you've got the possibility of subsurface oceans on Europa and Enceladus. And even out there in the Kuiper Belt, the larger Kuiper Belt objects, like Pluto, can have subsurface liquid water oceans. And the second you've got that, you've got the possibility for, we know that Pluto's geologically active. We know there's some sort of thermal source there to keep, it doesn't take much out there, but we know there's some sort of thermal source able to keep water liquid in its subsurface ocean. And we know that we see like thermal spots, geysers on Enceladus. And we know that Europa has its subsurface liquid water ocean because of the tidal stretching, very similar to what Io goes through. And there's the possibility that you may have those sort of, subsurface vents, the hydrothermal vents that are going on there. So, the habitable zone is probably all through the solar system, it turns out now. And that's even more stunning when you think about it, because that even adds more yet to the stage for the play of life out there in the galaxy. So, again, potentially habitable exoplanets. Here's a little update on that figure of different known, again, to scale. Here's our own system. There's our Earth and Mars and Jupiter and Neptune. And then artistic representations roughly of what some of these worlds, might kind of be like. Many of them are thought to be these, water vapor rich ocean planets. So they're depicted with these sort of, hazy water rich atmospheres that you can't see much on. But in terms of their size relative to our known planets, these are all planets around other stars in the habitable zones of those stars. So lots and lots and lots. So this is, kind of again another my artistic representation of, kind of an homage to the Kepler mission of what it's basically doing, looking for these transits that are going on. But here in our system, we've got Jupiter out there where it is at 5 AU or so, but Kepler is seeing a lot of these Jupiters in close. So it's kind of too bad because you got these beautiful, planets being detected where, in the habitable zone, 1 AU from the star, but they're gas giant planets. I don't know if you're going to have, cloud-based life up there. Maybe it could be. I don't know. But, if any of these Jupiter-like stars that are in close to their parent stars there have big moons like our Jovian planets do, you come up with the possibility that it's not the life on the planet. It might be that there's life on the moons of those planets. And so there's been this search in the Kepler data looking to see if they can peel away the possibility of detecting the moons around some of the transiting planets. Because, if you can get multiple observations of those transits, you might see that there's a glitch on one side of the transit on one time and a other glitch on the other side at the other time as the moons orbit around the planets that are going there. Well, it turns out that there is one planetary system they found so far that appears to be a moon going around the planet as well. The first exomoon yet discovered. So... yeah, right, exactly. And, from my perspective, it's kind of, as an artist as well, for me, it brings up all those beautiful sci-fi skies, Here is a depiction that I did of one of these systems, maybe with a moon. This is HD 99109, an actual exoplanet with a planet that's about half the mass of Jupiter orbiting its sun-like parent star 1 AU away. So imagine that. We don't know if that particular one has one of these moons, but this is my depiction of what it might be, if there was one there. Is it Titan-like? Is it Venus-like? I don't know. So the galaxy is pretty inventive. So if it's a system where there's a moon where it's pretty cold, your sky might look more like this. But there's all kinds of possibilities. Now, okay. Now, so far, we've been doing this conceit of sun-like stars, and we have this conceit in our head of thinking about our solar system being a single star system, but most of the stars in the galaxy are actually binary stars, okay? And it has turned out to be that a few of the stars that Kepler has detected planets around are binaries. Kepler 16 is a binary star system, and it is known actually to have a planet, at least one. And so NASA did a whole series of these sort of travelogue posters that were done in the sort of 1920s, steamer trunk travel era of travel, visit Bali, So they did a whole bunch of, ski the ices of Enceladus, and visit the rings of whatever. So they did one for this system, sort of this Tatooine-like, where your shadow always has company. And it's a great image and all, and it gets this idea across that you can have double shadows and all. But I put this up here because, again, as an artist, though, there's a flaw in this image. They goofed when they made the image. The artist goofed. What did the artist goof at? It's truly a system where one star is cooler and dimmer than the other star. That part's correct.
The star should be up on top.
The
Or does it should be lined up vertically?
Well, okay. I mean, I don't know what part of the orbital plane you're in here and where you are on the planet, if you're near the pole or whatever. I'm going to draw your attention to the shadows.
Shadows are bigger on the right than the system.
The colors. Somebody said the colors. Colors of the shadows are wrong. Okay? Think about that. Okay? The light, this big, bright star here, okay, is illuminating all of this area. Is the shadow being cast by this red star here, okay? So there's a shadow from this star coming across this way, but the cooler, brighter star I'm sorry, the hotter, brighter star is filling in all of that light, all of those parts of the shadows. The colors are backwards here, right? The red shadow should be this one, and the darker other shadow should be that one. So it's something called the Flammarion effect. It was a French astronomer who actually kind of started to really think about what the light and shadow would be like in a double star system, and imagining the extreme case, like Alberio, where you've got a really orange star and a hot blue star. Imagine that color contrast, and then think about what the colors of the shadows will be. You can see this yourself anytime you go to a room or someplace where they have multiple colored lights. You'll see these multiple colored shadows. Next time that happens, or do it yourself in your home. Put up a red light and a blue light someplace, and shine them, and look at your shadows and kind of see. It's like, oh yeah, the blue shadow is where the shadow is from the red light, and vice versa. Anyway, neat picture, great. I just used it as a learning, teaching moment about the Flammarion effect. So there you go. So, sorry.
Just to let people know, if you like these images, you can go to the NASA website and download the high-resolution versions and
Yeah,
get
to print them.
printed out. I have a friend who has a whole series of these across her wall printed out.
Yeah, they're really neat series.
Poster size.
Yeah, they're really fun. You can find them on the website. So yeah, many star systems out there. The planetary systems, the views are going to be more like this with double stars in the sky. That's Tatooines everywhere. Okay, so this is what got me into this, right? Thinking about the possibilities of life out there. Back in the 1960s, Frank Drake, who was working with Carl a lot in the earliest search for radio signals from other systems, came up with a kind of a formalism, an analytic formalism that we now call the Drake equation in his honor, to sort of try to pick apart the bits and pieces of this puzzle of how many other technological civilizations are there out there in our galaxy, right? How do you even start to begin to approach that question? How many are there? Well, he broke it down this way. It's a series of progressively multiplicatively small fractions of systems out there that might have intelligent life. And you start out by saying, well, just how many civilizations are out there? Well, the starting point is, well, how many stars are there in a galaxy? That's, if there's only 2 stars, you're not going to have many more civilizations than that. Well, how many stars are out there? Or conversely thought of, what's the average rate of star formation out there? You can think of it in 2 different ways. Well, we know that pretty darn well. We can do the stellar census of our galaxy, and it's a few hundred billion stars. Right? You ask some people it's 200 billion, you ask others it's 400 billion, but it's a few hundred billion stars. We know that number. And so what you do is how many stars are there? What fraction of those stars have planets? Of those planets, how many of them are Earth-like? Of those Earth-like planets, what fraction of those develop life? Of the ones that develop life, what fraction actually develop intelligence? Of those intelligent ones, what fraction get to the point where they can become a technologically communicative civilization? And then what fraction of that lifetime is that communication, that civilization actually communicating? And you multiply all that together, and it kind of, the idea was it would tell you how many other civilizations might be out there. Well, okay, we know how many stars are out there. The very next number in that equation for decades was unknown. How many planets are out there? We just didn't know, right? Some people would think, well, maybe making planets is kind of tough. I don't know. Maybe that's a low fraction. Some people were leaning more toward the higher end because we think it looks like planets are a natural byproduct of star formation, but we didn't know. 20 years ago, 40 years ago, we just didn't know. Now we know that number is about 1. It turns out now, because of Kepler and all these other searches, it looks like it's rare for a star not to have planets. Just about every star out there that you see in the sky has got a planetary system around it. Phenomenal. And that means the possibility for life all over the place. And so for me, as a space artist, fascinated with this, I get to go in my playground of digital tools and make all the habitable worlds I want. And so I can think about this all I want. So back in 2009, December of 2009, there was a movie with a bunch of tall blue people in it that came out. And for me, that was a godsend, because for all of my life up until that point, I'd been dreaming about what it would be for somebody to finally do it right and photorealistically depict what the botany and the biology on an exoplanet might be like. And you know, all the story things aside and all the other things aside that you might want to complain about, the artistry of Avatar for me was just phenomenal. And what was neat was the things that they went through in developing the ecosystems. It's kind of fun because Cameron's original ideas were that he wanted to really drive home how alien the botany was. And so it wasn't going to be just green plants like we have here on the Earth because of, you know, chlorophyll. Who knows what the photochemical reactive chemicals might be in these other alien plants. Maybe it's something that's more teal colored or magenta colored. And so here's an example where everything's more kind of on the bluish end of the spectrum. It's really cool and you can explore that and all, but from the movie making and storytelling perspective, however, they had to dial it back and not be very alien, because then you can't tell a story that the audience can really relate to well. You want a certain familiarity so you don't constantly feel like you're like, oh, what's going on here? You've got to relate to something when you're telling a story like that. And so they had to dial it back. But if you wanted to really crank it the other direction, probably where the reality is, you can start imagining some much more alien sort of biotas, because the nature of natural selection and evolution is this very random, chaotic sort of process that, you know, it's not going to be repeated once out there in the whole history of the galaxy, probably. And so anything even remotely resembling what we have is probably going to be unlikely. And so you're going to, you know, anything you can imagine as an artist is probably not alien enough compared to what some of these botanies might be like on other planets, let alone the you know, we're talking about the flora, let alone the fauna, okay? You might have Medusa planets out there with all kinds of weird stuff going on. There's all those water worlds out there, okay? What kind of alien subaquatic sort of things might be out there? You know, so yeah, it's true that the physical laws, the physical things that are going out there in the environment that drive evolution and natural selection and evolution are common. I mean, if you're something living in the water, you've got to be hydrodynamic. If you're living in the air, you've got to be light and fluffy and all that. Those things tend to drive you toward optimal engineering solutions. And there is this concept of convergent evolution, right? You evolve flight in a number of different episodes on the Earth. Insects got to flight, mammals got to flight, birds got to flight. And there are some commonalities there in terms of design, but the exact biological pathway that you get there is constrained by the quirks of history. The fact that the lobe-finned fishes that happened to crawl out had roughly 5 skeletal remnants in their lobes, and that's why we end up with 5 fingers, and that kind of quirk, right? So those details are probably never to be reproduced, while the overall basic ideas might be similar. So hydrodynamics, you know, fish-like things may be fish-like things, even though the details inside, the cellular structure, the exact shape and order of the things that are going to be like fins may be very different. So again, anything we as artists can imagine is probably not alien enough. And I just put in some fun things that I kind of was playing with and looking around at, and you know, again, not alien enough, I'm sure. So after all of this, and thinking about it and how alien some of these worlds may be, the whole reason for all of this is that it really puts us back in context. It tells us what's possible, and it puts our world and our biology and everything that we know in context. And I just wanted to end on this quote from T.S. Eliot. This is what it's all about. This is the best planet in the whole galaxy. I don't care how interesting all the other ones are. This is still the best one, okay? And that's what it's all about, is coming to that realization and understanding it in that way. So for all the fascination and for all the love of understanding what we're looking at in all these other systems out there, it's all about this. So I probably have talked way longer than I should have on that, but there you go. I'll leave it at that. Thanks. Questions? Any comments, questions? Yes?
So when you talk about the habitable zone, isn't it true that the magnetic field of the Earth shields us from a lot of solar radiation.
Yeah, it sure does, sure does.
Yet, I don't hear people talking about, like what's in the habitable zone, and are you able to look for and considering, so which ones may have magnetic fields that give
Yeah,
similar
exactly.
benefits?
Yeah, exactly. So I mean, it's like I said, it's one of many. That's why I tried to make the point that this concept of habitable zone just by itself, of you're not so close that the water's boiled away, you're not so far that it's all frozen. That's only one slice, one dimension down this corridor of what it is that actually makes a planet habitable. And it's I don't know how to quite say it, but it's not just the physics of where the Earth is and the fact that it has a magnetic field and it's at just the right temperature zone. It's life itself makes the planet habitable. It's a bizarre way to think about it, but it's sort of the Gaia hypothesis sort of idea that the biosphere itself continuously tunes things so that as the sun is slowly brightening, in its main sequence lifetime, that life on Earth is tuning the atmosphere of the Earth and the gases to keep maintaining that habitability. Whether that's actually true or not, we don't know, but it sure does seem like it at times. So it's a much more complex tapestry and fabric than just the simple calculation of, you're this temperature or that temperature. There's so many other things going on there. And now, as I tried to make the point, that it's even more than just that. I mean, you can be habitable out there even in the Kuiper Belt, for all we know. So I'm trying to get us to slowly start like retiring this concept of habitable zone, because I think it's too constraining. It's not imaginative enough. Yeah. Yes.
On that, when I talk about astrobiologists, and just look in the ocean, there's things we barely recognize. As
Yeah.
being alive.
Yeah. It's the most, to us terrestrial surface things, the most alien environment on our planet. And that's a common biological heritage, right? And so that's what I mean by even that stuff that in our ocean looks so alien to us is not even alien enough compared to what some things are probably going to be like out there. So yeah. I'd love to wrap your brain around that. Yes, sir.
Yeah, so is the nation. Is the Kepler still limited by distance? Can you look at suns on the other side of the galaxy, or are you still limited within a local region?
Yeah, it's kind of a magnitude limited thing, because you want the stars to be bright enough that you get the photometric precision on the detector to be able to detect those little dips, right? If you're way faint to begin with, there's just too much noise in the signal to get the dips that you need. So that's why it picked that region of the sky because it's in the plane of the galaxy where you've just got a lot of stars. But it's also it's a magnitude issue as well. So.
Brighter stars further away.
Well, yeah, I mean, it's a magnitude thing. Now, that can be an intrinsically brighter star far away or a dimmer star close up. But again, because Kepler's they're picking it of solar-like stars, a sort of G-class sort of main sequence sort of things. That puts a kind of a gate out there in the sky, because if you're looking in a magnitude range and then you're looking at this intrinsically solar-like type of star, there's only one distance or range of distances away from you where you're going to get that sort of part of the spectrum. So it's kind of a cloud, a zone out there in the sky. But that transit method will work for anything. It's only a magnitude precision issue. So you're not, I think the average kind of things, you're looking at things dozens to hundreds of light years away in that zone. So.
So what technology is limiting it from opening up that magnitude?
Probably next month's speaker will be better for that. But it's the capability of that CCD detector to it's the noise qualities of that CCD detector. Right? So having a very noise-free thing at very, very faint magnitudes. Frankly, it's not even so much that, because Kepler was more search area limited than where, I mean, it was only looking at one patch of the sky, imagine, too, right? So, do that over the whole sky, you got a lot more. That's what TESS is actually doing right now, the terrestrial exoplanet search that's going on. That's ongoing right now. It's an all-sky survey. Unlike Kepler, TESS is an all-sky thing. But I think there with TESS, it's a brighter limited, so you're looking at closer stars in general. So, yeah. Next month's speaker will tell you a lot more details about Kepler. So.
That's what you want to know. Well, it's slowly clearing out there.
Oh, very good.
See the moon, but that's about all.
currently it's still too bright to see anything, deep sky, maybe a few stars.
But the moon is way cool to look at if you've not seen it through a telescope. For those of you who are here,
So there is not a lot.
you got a little Terminator. There.
So we'll start with at least one telescope, because at least we've got many volunteers here that run the scope. So again, thank you.
Thanks again. Thanks everybody.